Hello everyone and welcome to this tutorial from the Computational Design Basics course at the Digital Design Unit of Technical University of Darmstadt. In this tutorial we're going to take a look at attractors. The attractor logic is a way to influence the geometry or the position of a set of objects based on their distance to another object. So let's get started. The principles of attractors in Grasshopper are very similar to the gravitational pull of the planet Earth. The further away we are from the center of the Earth, the weaker the gravitational force, and the closer we are to the center of the Earth, the stronger the gravitational force. So let's try to model that principle in Grasshopper. So let's start with an empty Rhino file and an empty Grasshopper file. And I will rename one of these layers and I will call it attractor. So that would be our Earth, planet Earth, attractor. I will make it a current layer and place a point in it. And then I'm gonna bring this point in Grasshopper by double clicking in the Grasshopper canvas, typing point to get the point reference component, set one point and select the point in Rhino. So our attractor is now in Grasshopper. Let's also rename it by right clicking on the component, attractor. And now we need an object that this Earth will pull. So let's make the purple layer the active one, the current one, and let's call it object, and let's place one point in that layer. And same like with the attractor, let's create a point reference component, set the point from Rhino, and we can call that objects. So we have attractor, we have objects, and now we need to determine the gravitational force, or the force with which this attractor is acting on the objects. So when we speak of forces, we need to also understand the concept of vectors. The force has a direction and a magnitude, and it's represented with vectors. So let's first understand how we can create a vector in Grasshopper. We have 2 points, and if we want a vector, what we can do is just start typing vector, and look what we get here. We have vector 2 points, so that should probably help us. Then this component needs the base point, the tip point, which is the end of the vector, and let's look at the u parameter later. So our base point is the attractor, the tip of the vector is the object. Now we've created the vector that goes from the attractor to the object. Let's also display it so we understand what we actually have. We can do that with vector display, and it also needs a base point or an anchor point. So let's use the same a that we pass to the vector, the attractor, and then it needs the vector. We can get it from here. If we now look in the Rhino window, we have an arrow with a very small arrowhead at the end that actually represents the direction and the magnitude of that force. The magnitude at the moment is equal to the distance between the points. Now let's look at this u parameter. The u input is whether to unitize or not the vector that's created. Unitizing a vector means setting it to the magnitude of 1 or the length of 1 unit. This is a Boolean. By default it's false, so we get the full length. Very easy way to set booleans is with a toggle, so a boolean toggle, and by default comes in as false. We can connect it. Now if I double click here, it becomes true, and you see our force vector is now with a length of 1. If I click it to false, again it's the full length. Maybe just to understand a little bit more about vectors, let's see how we can add vectors together. Let's imagine we have another object somewhere on the field, and I will create another point reference component. I will select that point from Rhino. So this is our second object, and we can basically copy that part of the definition, paste it, and just replace the object with the new object, and we get the new vector We can unitize it, same like the other one. Grasshopper treats vectors and numbers in the same way. We can use the component addition. Usually you use it to add numbers. You can use it to add vectors as well. So we want to add this vector, which will be vector A, with this vector, which will be vector B. And if we want to display it, let's just copy the display. Same reference point will be the attractor, but we'll just display the new vector. You see that it's a bit longer. Basically what Grasshopper will do is it will start following the first vector, and then from the point where it ends it will follow the second vector, and where it ends, that's the tip of the new vector, the sum of the two vectors. We can also visualize that by displaying the second vector not with the reference point of the attractor, but with the reference point of the second point here. And you see that that's the first vector, that's the second vector, and it ends up exactly where our sum vector is. And also what the vector looks as data, we can take a look by bringing in a panel. A panel is basically a text box that you can feed with data, either type in yourself or just connect it to a wire. A vector is a set of three numbers, just like a point, x, y, and z, that describe relevant to 0 where the vector points to. So we can copy only that first part of this definition, where the attractor and the object define a single vector, and disable everything else. You can save it for reference later. Let's define the objects on which the forces will act also in Grasshopper. An easy way to just get a random set of points within a region is to populate a 2D region component, or you can just type populate. And that gives us by default 100 points in a rectangular area with a width of 20 and a height of 10. Maybe we can change the rectangle, so I will right click and set the rectangle starting again at the origin. So I'll type 0, press enter, and click somewhere here. Okay, so these are our new objects. As you see, from each object the vector points from the attractor to the object itself. What we actually want is that the force acts from the object towards the attractor. We can do that by either swapping the A and the B inputs or reversing the vector. I'll reverse the vector just so you understand one more component to work with vectors. So reverse vector takes in a vector and gives us the opposite. It became a little bit unclear what we're actually getting, but we can help make it a bit more clear by changing the reference point with which we displace these vectors. Instead of the attractor, we are going to use the objects, and then you see that from each point we have an arrow pointing towards attractor. If we unitize the vector, that becomes a bit more clear. We have all these arrows pointing towards the attractor. Okay, so we are just seeing the force with which the attractor acts on the objects. We can, just for the sake of display purposes, create a circle in each object location. So these are the locations, and assign the size of that circle to be the force magnitude. At the moment they're all 1. We will change that because the gravitational force is actually dependent on the distance. Let's take in a number, and the length, which is here 1 for each vector, is going to be our magnitude. And then let's also connect it to the radius of the circle. As I move the point in Rhino, the sizes of the circles still doesn't change, but the directions in which the force acts is clearly changing. And then as next, we will actually start working on the magnitude of the force. Let's make some space here. If you don't want to move always components around, you can also use another thing. I'm just zooming a little bit out because it will affect the whole definition. You can hold the Alt and just click and drag, which will just create empty space in the Grasshopper definition. We want to determine the force. The formula for gravity is the mass of the two objects over the square of the distance between them. So the mass, let's assume the mass is 1, and we just need to find the square of the distance between them. But since we have unitized our vectors, we don't actually have the distance between the objects. So let's bring in a component that will help us measure it, which is called distance. And similar to the vector component, from 2 points, it takes point 1 and point 2, A and B, and it gives us the distance. Now we can square it. There's a component for that as well. If we type in square, that's the one we need. Compute the square of a value. Let's pass the distances here. So at the output here, we'll have the squared distances. But the relationship is reciprocal. 1 over the square distance. So we need to divide 1, and we are bringing in the division component. We need to divide 1 by the square of the distances. So B is our square distances, and in here we can set that to 1 by using the shortcut for setting a panel to be 1. The shortcut will be quotes for panel and then 1 for whatever you want to be in that panel by as it's created. So now quotes 1 creates a panel with a value of 1, which we can pass in here. So this is the squared, this is actually 1 over the squared distance. And if we pass it to the number that drives the radius of the circles, we can see that the circles that are closer to the attractor are a little bit bigger. The circles that are away from the attractor are actually very, very small. This is a good moment to save our file. Okay, so now that our files are saved, let's continue. We observe that the circles are quite small when we are away from the attractor and relatively okay in size when we are very, very close to the attractor. But we still haven't seen that reflected in the size of the vectors, because what we are displaying is still the original vectors with a length of 1. We can set the magnitude of the vector, Grasshopper calls it the amplitude, by using the amplitude component, amplitude, which requires the vector we want to set and the new amplitude or the new length, which comes in from the numbers component here. So let's connect that. We see that now the vectors are exactly the radii of all these circles. And here they're very, very, very small. So in order to change that a bit, maybe we want our attractor not to work exactly on the formula of gravity, as Newton defined it, but to still have a bit more smoother, not so sharp distribution or fall off of the force. To achieve that, we can use the GraphMapper component, which works like the graph of a mathematical function. And here we will connect the values we want to map to a function. So thus, in terms of mathematics, that would be the x values, and as an output we will get the y values, or whatever the function of x calculates for us. And there are some pre-built types, and to create what we want, we can use the Bezier component. Let's connect that output to the numbers. At the moment we see no difference because the Bezier by default is set to a linear function. What goes in, the same goes out, but we will change that. So let's connect that and start changing. I will pull this point, and also I will pull this point, and you see that as I'm pulling it, the circles further away from the distance, from the attractor, are also becoming to be more visible. If I pull this down, then we see that I'm actually shrinking the closer circles. And then one more thing that I would like us to have control over is actually how strong is the strongest force. We can do that by multiplying these numbers. Multiply. With a number slider. Number sliders in Grasshopper by default, if we just call in the number slider component, come in between 0 and 1 with 3 digits behind the decimal point. But if we type in, instead of slider, if we type in a number, let's say 5.5, that would give us a slider that's moving between 0 and 10 and set to 5.5. So let's use this. Actually, let's connect the output from the GraphMapper component. And this is our new force magnitude. It's quite big at the moment, but I can scale it down with this slider. Now I have a bit more control over what it is. We can sort it a bit so that we know what does what. And we will sort it in the following way. Here we are just displaying stuff. And the input that goes in is actually a vector, 2 times the same set of points coming in from here, and the size of the vector and the circles. So to make that a bit more explicit, I will type in a point reference component. I will connect it to the points and just use it 2 times here locally. And then I will make another one, which is a vector component, to explicitly create the input of the vector. We have the number, so that's kind of a unit at the moment. I will group it with Command G on Mac, or I think Control G on Windows. And I can right click on that group and rename it to call something like display. So this is good for documentation purposes later when you open an older definition. If it's structured a little bit and not just a mess of cables all across the canvas, it's a bit easier to start using it again. And what we will call this is our force logic. And again, to be a bit more explicit, I will take in a number to represent that it's actually based on the distance, so that would be distances. Use that number. And then this is another number. The output of that unit here, that block of components, is the force, attractor forces. Attractor forces. The magnitude of the forces. So I'm gonna group that and let's connect this here. Okay, and let's rename the group. Name the group to force magnitude. Okay, so that's a little bit tidier. Now we know what does what. And we don't need that slider. And we can copy that for our next step and disable the old copy. Let's imagine we don't want the force to act on all of the points, on all of the objects. And if they're beyond a certain distance, we don't want the attractor to influence them. So we're going to create a filtering logic now. And the filtering logic also works based on the distance, if the distance is below or above a certain threshold. So we have the distance, and let's use the smaller than component. The distance is coming in from here. Let's actually copy that so it's easier. We have the distances, and then let's define our threshold with a slider. I will double click and type in 15.5. Because the number is larger than 10, Grasshopper will give us a slider that is not between 0 and 10, but between 0 and 100. And if we actually want to redefine the ranges of that slider, if 100 is too big for us, we can double click on the label of the slider, and here we can set the minimum and the maximum. I will set the maximum to 20. And now we have a slider between 0 and 20. So let's see what actually this does. If you bring in a panel to display the distances, we can see that that is a collection of distances. In Grasshopper, that's called a list of numbers. And if we hover over the distances, we see 100 values inherited from one source. So there's 100 numbers in this list. If we go down, we see that the last number has the index of 99 and not 100. That's because in Grasshopper and in programming in general, the first item in a list always has the index of 0. I will copy that same panel and I will connect it to the output of the smaller than component. And what we can see here is that it basically tells us if the distance is smaller than the threshold, let's bring in the threshold here, it gives us true. If it's not smaller than it, larger or equal, then it gives us false. And as I'm controlling that slider, as I'm sliding it up and down, we see that this check happens in real time. So now we can use this pattern of true and false to kick out the objects that we don't want. This is done with the cull pattern component, culling a list. Cull pattern, which requires the list we want to cull and the pattern. The pattern is the true and false list, and the list we want to cull is actually the points that are coming from here. So let's create another point object, connect it here, and at the end we will have again points. So here 100 points are coming in, and at the end we have 23 points. If we select them, we see that the ones closer to the attractor are the ones that get copied. If I change that distance, then more and more get copied. If I reduce it, then at one point nothing remains. Okay, so this is filtering the points, and if we want to move that to the display, we can just connect the points that coming out of the filtering to the points that are being displayed. What we see though is that here we have some kind of a glitch in our definition, and the reason for that is that here are coming 14 points, and here are coming 100 vectors and 100 circle radii. Basically, once the 14 points are over, everything beyond 14, 15, 16 vector and circle are displayed over the last circle. This is quite important to understand at the moment, how Grasshopper works by matching the lists of data that feed the components. So we basically need to cull with the same pattern also the vectors and the numbers. And we can do that by copying the cull component and changing the list that comes in. That would be our vectors list first. That is here. Let's keep that same logic of making everything explicit. So I will create a vector at the beginning, which comes in here, which will actually feed the cull component. So these are our new filtered vectors. If we hover, we see that there are 14 vectors instead of 100. And next we need to filter the attractor forces. Again, copy that. I will have another number component. That would be the attractor forces. This is the list we want to cull. And another number component. These are the resulting attractor forces. Instead of 100, they are 14, and that feeds us into our display component. So here we have this logic, which I can combine into one group and call it filter. So that filters points out based on the distance from the attractor. Okay, so we have a well-structured definition that determines the force, filters out some of the objects, and then displays the result. And if we move the point that defines our attractor in Rhino at the moment, we can see that that is actually working independent of the location. For every location that's calculated anew. Let's create that a little bit more parametrically, the position of the attractor. What we can do to what we can do here is to actually place the attractor to travel along a path or a curve. So I will again copy that whole bit, disable the old copy. That way you have a nice overview of the steps that we took as we were developing this definition. And then zoom in here at the beginning where we define our attractor and our objects. And as I said already, let's try putting the attractor to travel on a curve. In Rhino, I will create a NURBS curve on a new layer. And let's call that layer Attractor Curve. And let's bring in the curve into Grasshopper, double click, type in curve to get the hexagonal icon for the curve reference component, set the curve to the one in Rhino. And now we need to find a point on that curve. A point on that curve. Basically, if we just type this, point on curve, we already get a component that will do that for us. And as you see, that is kind of a slider that goes between 0 and 1. And the input is the curve and the output is a point. If I have this selected, you see that we have a point here. Actually, to see the point a bit better, let's make a sphere around that point as a planet. The sphere component takes in a base plane, which can also be inferred from if we just pass a point, and the radius by default is 1. That's already okay for us. And as you see, if I'm sliding that slider that the point on curve component gave us, at 0 I'm at the beginning of the curve, and at 1 I'm at the end of the curve. This number is what we call a t parameter for curves. The t parameter describes location on that curve within the space of the curve, not the world coordinates, not the x, y, and z, but the space along that curve. It sees the curve as a line, basically one-dimensional space. 0 to 1. A more explicit way to do that, and I think that's quite useful for later on, is to actually use the component evaluate curve, this one here. It works in the exact same logic, but it gives us a bit more control and a bit more information. In C, we connect the curve, and in T, we define the T parameter. I can use a slider, as you see, by default 0 to 1, so same as the slider that comes in here, that helped us navigate from the beginning to the end. And let's connect that to T, but see what happens. If I'm at 0, I'm at the beginning of the curve. However, if I move it to 1, I'm not at the end. I'm somewhere along that curve. In order to force the range to be from 0 to 1, we need to reparameterize the curve, which is done by clicking either here on that curve parameter or on the source parameter. I'll click here and click reparameterize. This icon appears, which tells us that that curve has been reparameterized. And now, as you see, 0 means the end, and 1 means the end, and 0 means the beginning of that curve. We can actually use that point as our new attractor. And since we want to build a sphere in the attractor, let's connect the attractor component to the sphere. We can drop that. Okay, so we have an attractor that travels along that curve. And as you see, as we're moving it, circles are changing in sizes and are popping in and out. To visualize that a bit more explicitly, how we filter the points, let's create lines between the attractor and the points that get filtered. We can create a line in Grasshopper in many ways, but the one we want is a line between 2 points. So that's the one. And the first point will be the attractor, which is all the way here. And the second point, and since we're using the display, the second point is the points where our filtered circles are. As you see, that created a set of lines only between the points we filtered and the attractor. Now if I move in the attractor, you see that that's kind of a spider that's crawling along that curve, snapping to the closest points in that field. Let's see what if we don't want a point to act as an attractor, but maybe we want to model a street that is the attractor, so it's something that has the shape of a curve. Later on we will see how we can use also surfaces to act as attractors. So the whole curve acts with a pulling force, or exercises some kind of an influence on the object we want. So again, I'm going to copy what we have, disable the previous one, and now let's see how we can use an object that is not a point, a curve object, as the attractor. Basically, since the attractors work based on distance between the attracting object and the objects we want to influence with the attractor, we simply need to measure the distance between all our objects and the curve. Let's take that same curve, let's drop the sphere. Instead of evaluating it into a point, let's use the curve. So the distances between the curve and all of these objects we can find by using the component closest, curve closest point. The curve closest point needs a curve and a set of points. And as you see, for each point it found a point on the curve that was the closest, which means the shortest distance, and we get that here. So now we have all the distances and all the attractors. Each of these points on the curve corresponding to a particular object here is actually its own attractor, own private individual attractor. So we can use that result here, all these points, as the attractor points, and we can use all the distances that coming from D instead of the distances that we use here. So to do that, I'm just going to connect 1, the distance here, and 2, the distance here. Looks kind of messy at the beginning, but let's see why. First of all, let's disable the lines for now and see whether the attractor logic actually works first, and then we'll sort the lines. We can disable the preview of that so that we only see the curve. If it's very close to the curve, the point has a bigger circle. All the vectors are pointing towards the line, and if it's a little bit further away, it's smaller, and it's really far away, then there is nothing. So the same logic applies, but now we're using a curve as an attractor. Now let's go back to these lines that are kind of misbehaving apparently. So lines, what do they connect? They connect 100 points here with 60 points here. What did happen? We forgot to filter the attractors in the same logic as we filtered the objects. And we need to filter the attractors at the moment because each point from the objects has its corresponding attractor that is the closest point on the curve. So we can copy the culling component here, connect our attractors, or let's make it a bit more explicit. Let's take in a point component, connect our attractors, connect the list. That would give us a filtered set of points which has 60 values. Great. And that's our new A point for the line. So you see now that's way more tidier, and it's actually what we expect. Each point is connected with a line that goes perpendicularly to the curve in that location. And as we change the line, or as we change the threshold of distances, we will see that being adapted in real time. Now, a nice way to include these new components into that group is to select them, right-click on a group, and add to group. So now this is all grouped together. This is our new filter group, extended with one more thing. And then our display group is actually extended with the line. So let's right-click and add to group. Now also the lines are included in that group. And that's it. Thank you for watching this short introduction to attractors in Grasshopper. Thomas will take it over from here and build with you two examples, one an urban and one a building design scenario that make use of attractor logic.